So, hello everyone, my name is Mohammed Al-Khuffash and my colleague
Ramadan Shweki
will give a brief overview on electronic control units, ECUs, in modern vehicles. ECUs act much like a brain of modern motor vehicles, as they provide instructions for various electrical systems, instructing them on what to do and how to operate. Specifically, an electronic control unit ECU is any embedded system in automotive electronics that controls one or more of the electrical systems or subsystems in a vehicle. The terms control unit and control module are used interchangeably in the literature. Some manufacturers prefer one over the other, while others use both terms with no differentiation. Technically speaking, there are no differences between them. For the purpose of this video, we'll just call it Electronic Control Unit, ECU, to avoid any confusions. Now, my colleague Ramadan Shweki will tell us about the history of ECUs.
The first electronic control units were developed in the 1970s. Back then, the aim was to make use of new technologies to help in the development of safe, clean, and economical cars. The pursuit of economic efficiency and cleanliness was closely linked to other customer benefits, such as driving pleasure. Air pollution in major cities was becoming a big problem in the mid-20th century. This was characterized by the European diesel boom, which forced car manufacturers to accelerate the adoption of electronic control of car engines in an effort to produce a better fuel burn. Technical developments in semiconductor technology support ever more complex functions to control ignition timing and adjust the air-fuel mixture. In the early 1980s, with the introduction of fuel injection, the ECU took on a new role of being completely responsible for the fuel and ignition management of petrol engines. Closed-loop lambda control was soon included, and the ECU rapidly began a new era in engine efficiency. Roughly at the same time, the anti-lock brake system ABS was introduced and underwent continually development to such an extent that it is now fitted as a standard on every vehicle in Europe. During the 1990s, the ECU started handling vehicle security. It was also beginning to appear on diesel engines, which played no small part in the success of the turbo diesel engine over the next couple of decades. The latest developments also take comfort into account. Many kinds of new functions appear in conjunction with driver assistance systems. Their scope extends far beyond today's standard features, such as park pilot or electronic navigation systems. The aim now is to produce the sensitive vehicle that uses sensors and electronics to detect and interpret its surroundings.
Modern motor vehicles are equipped with a vast array of electronic circuitry to manage operation of the vehicle and to ensure the safety of the occupants. In fact, a modern motor vehicle can have up to 80 ECUs. Each of them serves a specific purpose. For instance, we have Engine Control Module, ECM. It's also called Engine Control Unit, ECU. For the purpose of this video, we'll just call it ECM to differentiate it from the Electronic Control Unit. We also have Transmission Control Module, TCM, Brake Control Module, BCM or EBCM, Airbag Control Module, ACM, Telematics Control Module, and many other control units that control several functions of modern vehicles. Taken together, these systems are sometimes referred to as the car's computer, even though they are not a single computer, but multiple ones. Sometimes, one assembly incorporates several of the individual control units. For example, Transmission Control Module, TCM, and Engine Control Module, ECM, can be combined in a single unit called the Powertrain Control Module, or PCM. One can easily figure out, just from their description, what each of these modules does. Nonetheless, let's take a brief overview on how they work. The ECM is the heart of the engine management system. It controls fuel supply, air control, fuel injection, and ignition. It does that by reading values from a multitude of sensors within the engine bay, then controlling a series of actuators on an internal combustion engine to ensure optimal engine performance. An actuator is basically a component that's responsible for moving and controlling a mechanism or a system. For example, opening and closing a valve. We will talk about some of the sensors that ECM uses later in this video. TCM controls modern electronic automatic transmissions. It typically uses sensors like vehicle speed sensor, wheel speed sensor, throttle position sensor, and other sensors in the vehicle, as well as data provided by the ECM. After getting the required data, TCM then calculates how and when to change gears in the vehicle, ensuring optimum performance, fuel economy, and shift quality. BCM manages the brake system in the vehicle. In modern vehicles, BCM is a part of Electronic Stability Control, ESC, which provides two active safety systems: the anti-lock braking system, ABS, and the traction control system, TCS. ABS prevents the wheels from locking during braking, while TCS prevents the wheels from spinning when starting off and accelerating. ESC recognizes if skidding is imminent and intervenes very quickly. An ECU monitors the signals from sensors like steering angle sensor, wheel speed sensor, and other sensors, and checks about 25 times a second whether the driver's steering input corresponds to the actual direction in which the car is moving. If the car moves in a different direction, ESC detects the critical situation and reacts immediately and independently of the driver. It uses the vehicle's braking system to steer the vehicle back on track. With these selective braking interventions, ESC generates the desired counteracting force so that the car reacts as the driver intends. ESC can also intervene on the engine side to accelerate or decelerate driven wheels. So within the limits of physics, the car is kept safely on the desired track. ACM is a control module that controls the supplementary restraint system, also known as airbag system in the vehicle. The ACM determines when to deploy the airbags in the event of an accident. It extracts data from multiple crash sensors around the vehicle and decides if the crash impact warranties a deployment of the airbags. This needs to happen within milliseconds after the impact in order to ensure maximum safety to the occupants. After seeing what roles ECUs can play in a modern vehicle, let's take a look at the design architecture and specifications of an ECU. The design of an ECU involves both hardware and software to perform the functions expected from that particular module. The control program is stored in a special memory and implemented by a microcontroller. The control unit and its components are referred to as hardware. Most of the hardware components of an ECU are surface-mounted on a printed circuit board, PCB. The PCB is installed in a housing of plastic or metal. The housing is designed to withstand very high demands, such as extreme ambient temperatures. It can be in normal vehicle operation as low as -40 degrees or as high as 125 degrees. These temperatures can also change extremely. ECUs may also be subjected to indirect materials and supplies, for example, oil or fuel. They should work properly under mechanical stress such as vibrations from the engine. It's highly important for the ECUs to be adequately sealed to prevent environmental influences from affecting the performance. A multiple plug connects the control unit to the sensors, actuators, and electrical power supply. The design provides extremely efficient use of space in low-weight packages. An ECU is basically a microcontroller, which consists of the following components. Central Processing Unit, CPU. This contains the control unit and the arithmetic and logic unit. The control unit executes the instructions from the program memory, whereas the arithmetic and logic unit performs arithmetical and logical operations. A typical ECU can use 8, 16, or 32-bit CPU architecture with up to 56 MHz clock speed. Semiconductor memories. Semiconductor memories, which store data like digital signals, program code, variables, and constants, play two main roles in a typical ECU: as a program memory and data memory. Program memory is a read-only memory in which the operating program is permanently stored. It's typically ROM, PROM, EPROM, or flash EPROM memory. Data memory is accessed for reading and writing, also known as RAM. This contains the data that's currently being processed. Non-volatile memory, like EEPROM, is used for the data that must not be deleted when the supply voltage is switched off. Additionally, there are input and output devices, I/O devices, which handle the exchange of data with peripheral devices. Peripheral devices include the secondary devices that send and receive data to and from the ECU. These include external data storage media, for instance. There's also a bus system, which connects the individual elements of the microcontroller, and a clock generator or oscillator that ensures that all operations in the microcontroller take place within a defined timing pattern. Finally, there are logic circuits, which are modules integrated in individual I/O units. They can handle specialized tasks such as program interrupts. The hardware specifications of an ECU may not sound that much, especially compared to a typical computer or even a smartphone. But ECUs run much more efficient codes. Speaking of which, let's talk about the software that runs on a typical ECU. One of the requirements on electronic systems is the real-time capability. This means that control procedures must react to input signals within an extremely short time. For example, a wheel that has a tendency to lock must be detected so quickly that the ABS control algorithm in the control unit can reduce the brake pressure via the hydraulic modulator quickly enough. The complexity of an electronic system, therefore, makes extremely high demands on the software that's developed. The machine code is stored in the program memory where it remains permanently. The CPU accesses these components via the bus system, as it reads the numerically coded commands and executes them sequentially. The time taken to read in and execute the command depends on the microcontroller and the clock frequency. The microcontrollers that are currently used in vehicles can execute up to 1 million commands per second. Because of the limited speed at which the program can be executed, a software structure is required with which time-critical functions can be processed with high priority. The engine management program has to react extremely quickly to signals from the speed sensor, which records the engine speed and the crankshaft position. These signals arrive at short intervals that can be a matter of milliseconds, depending on the engine speed, of course. The control unit program has to evaluate these signals with high priority. Other functions, such as reading in the engine temperature, are not as urgent, since the physical variable only changes extremely slowly in this case. As soon as an event occurs that requires an extremely rapid response, the program that's currently running must be interrupted. This can be done using the microcontroller's interrupt control facility. Events can trigger a program execution interrupt. As a result, the program jumps and executes the interrupt routine. This is a piece of code for handling the interrupt. When this routine has been executed, the program resumes at the point at which it was interrupted. In reality, the control unit program has to react to several of these interrupts. Thus, an interrupt source can request an interrupt while another interrupt routine is currently being executed. To solve this problem, every interrupt source has a fixed priority assigned to it. Interrupts with higher priority are allowed to interrupt the lower priority ones. For example, the interrupts that has to be handled by an ECM are ordered from higher to lower priority as follows. Tooth interrupts. These come from the crankshaft position sensor that's located on the crankshaft's pulse wheel in order to obviously record the crankshaft position. Combustion synchronous interrupt. These are the calculations that have to be performed for combustion cycles. Ignition interrupts. The interrupts for igniting the spark plugs within a certain crankshaft range. The time frame. These are the control algorithms that have to run within a certain time frame, like lambda controls. And last but not least, background programs, which are all other activities that do not run in an interrupt routine. Because of the extensive variety of vehicles with different control programs and data records, it's necessary to have a system which reduces the number of control unit types needed by a given manufacturer. To this end, the Flash EEPROM's complete memory area can be programmed with the program and the variant-specific data record at the end of the production. This is so-called end-of-the-line or EOL programming. Another way of reducing the type diversity is to store several data variants in the memory, for example, transmission variants, which are then selected using coding at the end of the production line. This coding is stored in an EEPROM memory.
You may ask yourself how the software of ECUs is being developed. In fact, a study demonstrates that approximately 60% of the time spent on ECU development has to be devoted to creating the necessary software. A depiction of the development steps in the form of a V-model serves as the basis for all software development activities. This model is used to detail the process steps which facilitate implementation within a product development department. Quality assessments are scheduled at defined points of the development process for the purpose of process monitoring. At the start of vModel, the system is initialized and functional specifications are analyzed. At QA1, the resources are checked like capacity, development, environment, responsibility. After that, function is initialized and function specification check is performed. After function implementation, a review of each individual function and checking of following documents: specification, function description, source code, data definitions, and test documentation. Before the software delivery, the system is tested and integrated. All QA2F documents are reviewed. At the end, hardware and software are reviewed before the start of series production. An essential part of the development process is also the distinction between specification and implementation. This separation allows programming by contract, whereby project teams use the software knowledge of reuse teams who implement the functions for various customers. The scopes and levels of testing of the individual functions are determined in the Project Specific Quality Plan (PQSP), with the customer requirements in mind. In order to ensure that the created software can be reused to the greatest possible extent, there are C programming guidelines binding all programmers which are called up in the relevant reviews, for example QA2F. Due to the continuously increasing number of ECUs, with each function in a vehicle having its own system, it was necessary to develop and establish an open and standardized software architecture for electronic control units. An automotive open system architecture, AUTOSAR, was developed by worldwide partnership of automobile manufacturers. What will AUTOSAR provide? AUTOSAR provides a set of specifications that describes basic software modules, defines application interfaces, and builds a common development methodology based on standardized exchange format. Basic software modules made available by the AUTOSAR layered software architecture can be used in vehicles of different manufacturers and electronic components of different suppliers, thereby reducing expenditures for research and development and mastering the growing complexity of automotive electronic and software architectures. Based on this guiding principle, AUTOSAR has been devised to pave the way for innovative electronic systems that further improve performance, safety, and environmental friendliness, and to facilitate the exchange and update of software and hardware over the service life of the vehicle. It aims to be prepared for the upcoming technologies and to improve cost efficiency without compromising quality. AUTOSAR uses a three-layer architecture. Basic software offers services needed to run the functional part of the upper software layer. Runtime environment for the inter and intra-ECU information exchange between the application software components and between the basic software and the applications. Application layer that interact with the runtime environment.
On a very basic level, an ECU is fed with several inputs. The data from these inputs is assessed by the ECU and compared against stored onboard data. The ECU then decides what needs to happen to ensure the system functions properly and issues new commands to suit. These outputs then alter the operation of the system, delivering the desired effect. In their role as peripheral components, the actuators and the sensors represent the interface between the vehicle and the control unit. The electrical signals of the sensors are routed to the control unit via a wiring harness and the connector plug. These signals can be one of the following: analog input signals. Within a given range, analog input signals can assume practically any voltage value. Examples of physical quantities which are available as analog measured values are intake air mass, battery voltage, intake manifold and boost pressure, coolant and intake air temperature. They are converted into digital values by an analog digital converter in the microcontroller of the control unit and used for calculations by the microcontroller's CPU. The maximum resolution of these analog signals is 5 millivolts. This translates into roughly 1000 incremental graduations based on an overall measuring range of 0 to 5 volts. Digital input signals. Digital input signals only have two states. They are either high or low, or logical 1 and logical 0 respectively. Examples of digital input signals are on-off switching signals, or digital sensor signals such as the rotational speed pulses from a Hall generator, or a magnetoresistive sensor. Such signals are processed directly by the microcontroller. Pulse-type input signals. The pulse-shaped input signals from inductive-type sensors containing information on rotational speed and reference mark are conditioned in their own control unit stage. Here, spurious pulses are suppressed and the pulse-shaped signals converted into digital rectangular signals. The microcontroller uses output signals to control output states that usually provide enough power for connecting the actuators directly. It's also possible to actuate certain output stage relays for consumers that use up a great deal of power, like motor fans. The output states are proof against short circuits to ground or battery voltage, as well as against destruction due to an electrical or thermal overload. Switching signals. Actuators can be switched on or off using the switching signals. For example, motor fans. PWM signals. Digital output signals can be in the form of PWM, pulse width modulation signals. These are constant frequency rectangular signals with variable on times. Various actuators can be moved to various operating positions using these signals. For example, exhaust gas recirculation valve, boost pressure actuators, and so on.
There is a great number of sensors at work in motor vehicles. They act as the sensory organs of the vehicle and convert input variables into electrical signals. These signals are used in control and regulation functions by the control units in the engine management, safety, and comfort systems. Various measuring concepts are applied depending on the task. I will give you some examples on some of these sensors and tell you how they work. Throttle position sensor, used to monitor the air intake of an engine. The sensor is usually located on the butterfly shaft so that it can directly monitor the position of the throttle butterfly valve and how it is oriented so that the engine knows how much air is flowing in. How does the ECM know where the throttle position is? Within the throttle position sensor, there is a potentiometer. And what this does is, there is a wire running in and a wire running out. It's leading to the ECM. Within this potentiometer, there is a needle connected with a butterfly valve. As the butterfly valve opens and closes, it moves this needle up and down. So what happens is, as you move that needle up, it has to pass through more of this resistive wire element. The current is going to go through this needle and passes this resistive wire element and back to the ECM. Now, when the path is changed, more resistance is added. There will be a voltage change. The ECM going to measure that voltage change and use that input for various functions. For example, traction control, transmission control, fuel injectors, and cruise control. It's a very simple idea, and it's just you add more resistance, and that resistance change is a measurement for the ECM to know how to add more fuel or use less fuel. Mass airflow sensors are used to determine how much air is going into an engine, so that the ECM know to tell the fuel injectors how much fuel to inject to keep a good air-fuel ratio in the engine. What is inside it are these little circuits, and between these wires there is hot wire elements and a current going to pass through these elements, and air is going to flow through this. We want to keep this element at a constant temperature. By doing that, we can know how much airflow is going into the engine. What happens is, you step on the gas and you have got more air going into the engine. Well, more air is going to pass through, and the current is going through this, which is heating up this element. When that air passes through that airflow up, the temperature of this element is going to cool down. Now, temperature and resistance are directly related for this element. As its temperature drops, its resistance will also drop. And then the current is going to go up. That's going to heat up this element, so it's going to bring the temperature back to where it was. Now, what the ECM does, it translates this current into voltage change, and with that voltage change, it knows there's difference in airflow. Since it knows there's a difference in airflow, it can say to send more or less fuel. Crankshaft sensor. It must be close to the crankshaft to monitor the position or rotational speed of the crankshaft. The crankshaft position sensor detects crankshaft position and sends a signal to the ECM. The ECM calculates the injection timing, ignition timing, and the engine RPM according to the crankshaft position sensor signals. There are three types of crankshaft position sensors: Hall IC type, inductive type, and the optical type, mainly located at the distributor. It consists of LED photodiode and rotational slit, and it monitors the crankshaft position depending on the slit location. The camshaft sensor is used to relay the exact position of the camshaft to the ECM for specific cylinder event information. This includes what stroke the cylinder on, when to inject the fuel, and when is the optimal time to ignite the air-fuel mixture. Without this detailed information, new model vehicles wouldn't be able to achieve advantages of lower fuel consumption, lower emissions, and increased horsepower. This sensor is placed in close proximity to a tumor or relector separated by fixed air gap. This sensor is supplied with a high and low reference, with the sensor returning the signal to the ECM. Oxygen sensor is used in order to create a closed loop operation. What is closed loop operation? The closed loop operation is used to make sure that you are using the right air-fuel ratio. The ECM is going to take information from multiple sources. For example, throttle position sensor, MAF sensor, MAP sensor, and air intake temperature sensor. The ECM is going to read that information, and it's going to come up with a proper air-fuel ratio. It sends that air-fuel ratio to the engine, and then the exhaust comes out and it's going to come in contact with the first oxygen sensor. What does the oxygen sensor do? It sees if there is any oxygen left in the exhaust, it's going to tell the ECM that there is oxygen in the exhaust, you need to inject more fuel. Or there is no oxygen in the exhaust, you need to inject less fuel. That's the closed loop operation. There are two sensors, one before a catalytic converter and one after a catalytic converter. The O2 sensor is going to read the oxygen on the outside of the exhaust. It's the atmospheric oxygen, and the oxygen on the inside of the exhaust. What happens is, as this exhaust passes through the sensor, it creates a voltage spike. There is a difference in the amount of oxygen on the outside than there's on the inside. The ECM interprets this voltage difference as rich or lean air-fuel mixture. Example: if there is not any oxygen in here and there is a plenty of oxygen outside, there is going to be a larger voltage spike, and the ECM will read this as rich. If it is rich, you will have a higher voltage. If it's lean, that means if there is the same amount of oxygen on both sides, it's going to have a lower voltage. What does the ECM do with that? It says the voltage is high, then it injects less fuel. The voltage is low, it will inject more fuel. What does the other sensor do? Is to measure the efficiency of a catalytic converter. Last but not least, we want to talk about the future of ECUs. In today's vehicles, a controller area network, CAN, is used as a standard of vehicle network protocol. It may arise the problem that network bandwidth is insufficient in CAN due to traffic increase with improving vehicle systems. Accordingly, the vehicle network is introducing Ethernet. Vehicle network speed communication and distribution can be improved drastically by introducing Ethernet. Moreover, Ethernet allows better cooperation between various devices in the vehicle as Ethernet is more versatile than CAN. Recall, a modern car can have well over 80 computer systems monitoring and controlling everything from ride handling to onboard entertainment and communication systems. But in the next few years, there will be an astonishing number of ECUs in modern vehicles, more than 125 ECUs. The biggest challenge for automakers is creating autonomous vehicles, which will add the growing number of computers found inside a car. Autonomous self-driving will need significantly more processing power and sensors like radar cameras than today's vehicles. However, all these units take up valuable space, complicate certification testing process, and increase the cost and weight of vehicles. So how can the number of ECUs be reduced without sacrificing functionality? The answer is ECU consolidation. Designing a single high-performance ECU to execute the functions of several systems. That means placing all the control units in the same box, rather than having them spread throughout the car. This approach offers several benefits, including lower cost, less weight, and increased security. With fewer ECUs, there are fewer hardware platforms to manage, so automakers can more easily add new software-defined features and update existing ones. Software-defined ECU can replace fixed-function ECUs, the so-called virtual ECU, VECU. The VECU is loosely coupled with hardware, making it far more portable than fixed-function ECUs. The benefit is that an existing VECU can run on future platforms with few or no changes, and automotive designers can choose to run a VECU on various consolidated ECU within the same vehicle. In addition, software engineers may find it easier and faster to develop new automotive applications because they do not need to learn the low-level details of the hardware platform. As Pete Heighton said, the cars as they are, with energy recovery systems, for a human being are pretty undrivable, unless you have the technology there to make them drivable.